In this video, I'm gonna solve two more problems, 93 and 104. Please try to solve these problems before seeing the rest of the video. I would say spend at least 10 minutes for any of them. Okay, in problem 93, we have this half a ring at this condition, in this orientation, which is pinned to the wall at point O. Also, we have a torsional spring here, and this torsional spring at this moment is rotated 90 degrees. So if we release it, this torsional spring is gonna push this back, push the ring up. So at the beginning, everything is stationary, and we suddenly release it. And when the ring goes to this horizontal direction, or after rotating 90 degrees, the angular velocity of it is going to be 4 radians per second. So omega of the ring, and in this condition, is going to be 4 radians per second. And the question is, what is the constant of this spring? What is kT? To solve this, again, we are going to use work energy equation. T1 plus V1 plus U prime from 1 to 2 is equal to T2 plus V2. Kinetic energy at the beginning is 0. Potential energy, if I put my coordinate at this point, if I put reference line, at this point, the gravitational potential energy is going to be mass times g times height, which is negative r. So I'm going to have negative mgr. And also, we are going to have potential energy in the spring as well. And the potential energy in the spring is 1/2 of k times rotation squared, or deformation, angular deformation squared. And the angle is pi over 2, right? It is compressed by pi over 2. So pi divided by 2 squared. So these together are going to be the potential energy at the beginning. U prime from 1 to 2, the only non-conservative force we have is the reaction force, and they are not doing any work. So U prime is going to be 0. Is equal to T2 plus V2. So kinetic energy is going to be 1/2 of I about O times omega squared, because everything is rotating about point O. So we can use this equation for kinetic energy. Plus V2. And again, we have spring, and also we have gravity. The energy in the spring is going to be 0 because it's completely released at this point, because it was compressed by 90 degrees. So it is gone. The potential and gravitational potential energy, the centroid is going to be here, centroid of the ring. And based on the table, the distance of it is going to be 2r divided by pi. So this is going to be the new height for the centroid. And V2 is going to be mass times gravity times 2r divided by pi. And this k is kT, k of that torsional spring. So what is I/O? I showed you in previous videos. I of half a ring, about this point of it is going to be 2mr squared. I about the center of the circle is going to be mass times radius squared. So I/O is 2mr squared. So if you replace I/O with this, we have everything here. Omega is given, mass is given, r is given. The only unknown is kT. So we can find, after putting all the numbers, we can find the constant of that torsional spring, which is going to be 3.15 Newton meter per radian. The other problem, problem 104. Here we have this ring and this wheel. The mass of the ring is 4 kilograms, and also we know the radius of it, 250 millimeter. And also this bar, the centroid of it is a G, and also the mass of it 3 kilograms. We also know what is the radius of gyration, about point O. Radius of gyration of this bar about point O. So if the radius of gyration is Rg, for example, if you remember the definition of it, it's I divided by mass root square, right? When it says radius of gyration about point O, it means IO divided by m root square. So I of this bar, only for the bar, about O is going to be mass times radius of gyration squared. And radius of gyration is 350 millimeter here. That's the meaning of radius of gyration about point O. So we are releasing the system from rest at this point, and it's going to come down because of gravity, and there is no friction here. And the mass of these spokes, those little bars, is equal to 0, negligible. And the question is, what's going to be the velocity of point A at this point? So this is our first condition, this is second condition. And we want to find the velocity of A here. Of course, we are going to use work energy equation. So T1 plus V1 plus U prime from 1 to 2, which is 0. There is no conservative force that is working, is equal to T2 plus V2. So T1 at the beginning is equal to 0, of course. There is no movement. And I'm going to put the reference line here. So T1 is equal to 0. V1 potential energy is going to be 0 as well. U prime from 1 to 2. Do we have unconservative force here? Of course we do. We have OX and OY, two forces here, but they are not doing any work. But some of you may ask, how about the friction force here? The friction, we have a friction force here, and friction, of course, is not a conservative force. But why the friction force is not doing any work? If you have a friction force, but you don't have a slip, then friction force is not going to do any work. This is a very important point. I'll explain it in another video later. But here, based on the problem, this roller is going to just roll without any slip here. And because there is no slip, the friction force is not going to do any work. So U prime is going to be equal to 0, 2. So this is 0, this is 0, and this is 0, 2. So the only thing we need to do here is calculating T2 and V2 and adding them together. It must be equal to 0. What is T2? We have two parts here, the rod and also that ring. We need to calculate kinetic energy of any of them, each of them, then add them together. The kinetic energy of the bar is going to be 1/2 of IO times omega squared, omega of the bar. But what is the omega of the bar? Omega of it is going to be the velocity of point A divided by this radius, right? So omega of the bar is going to be VA divided by 0.5 meter. So we know what is omega in terms of velocity of A, which we are looking to find it. So T2 for the bar is going to be 1/2 of IO times omega squared, which is velocity of A divided by 0.5 squared. How about for this one? How about for the wheel or for the ring? We can say, we can actually do it different ways, but probably the easiest one is this. The kinetic energy of the wheel is going to be 1/2 of mass times velocity squared, velocity of the center of it. And also it's gonna have a rotational, it does have a rotation, so we are gonna have kinetic energy for the rotation of it too. And the rotational, the kinetic energy for the rotation is 1/2 of I about the center times omega of the wheel of this ring squared. But what is the omega for the ring? Omega for this ring, or hoop, whatever you want to call it, is going to be the velocity of A divided by the radius of it, because we have no slip here, right? Whenever you have a wheel which is rolling without a slip, the velocity of the center of it is going to be r times omega. R is 250 millimeter, so omega is going to be VA divided by 0.25. So let's write it down. The kinetic energy for the ring is going to be 1/2 of the mass of the ring times velocity squared, velocity of the centroid, which is VA, plus 1/2 of IO. And I for a ring is mass times radius squared. So mass of the ring times 0.25 squared times omega squared. And omega is velocity of A divided by 0.25 squared. That's the total kinetic energy. The first part is for the rod, and these two parts, they are for this ring. And V2, both of them are coming below the reference line. The kinetic energy for the bar is going to be negative mass of the bar times G times the height of it is going to be 0.3, negative 0.3. So negative mg times 0.3 m of the bar. For the wheel, the centroid of it is going to be here. So it's going to be negative m of the ring times g times 0.5. So T2 plus V2 must be equal to 0. And if you look at these two equations, the only thing we don't know here is VA. So just add them together, calculate this IO, and replace these M of the bar and ring with their value, which are given. Then you're going to be able to find velocity of A. So if you do the math correctly, velocity of A is going to be equal to 2.45 meter per second.